Okay, hello everyone again. Welcome to this session today about exploring .NET memory management. The idea of this talk is not to dive deep into how .NET memory management works, but we will of course have to go a little bit deeper into how it works, because that's the point of this talk, right? I want to go into how it works and how you can write your code so that you don't have to care too much, or that you can improve the memory behavior of your application when writing .NET code. So quick question, who of you is a .NET developer? I hope everyone here is. Okay, good. So yeah, we'll see how we can make our code run faster and run better when you're writing your code. So I'm Martin Baljouw. I'm a developer advocate at JetBrains, and I focus on web technologies and .NET. I blog about those things, and you can also add me on Twitter if you want, and reach out afterwards. So let's talk about the garbage collector. The garbage collector is one of the things in .NET that helps your application run. So what the garbage collector does is that it provides virtually unlimited memory for your application. So if you look at, for example, C or C++, when you write an application, you have to, whenever you want to allocate a variable in memory, you have to ask the operating system, can I please get some memory? And then the operating system gives you some memory that you can use. And when you're done, you have to give it back to the operating system, because if you keep onto it, memory will exhaust and you can no longer get any new memory from the operating system. In .NET, that's kind of different. .NET gives you the illusion that memory is unlimited. So what it does is, when your application starts, .NET will ask the operating system, can I get a big block of memory? Then the operating system says, yes, of course, I can give you a big block of memory. And then .NET manages its own memory inside of that big block that it just received from the operating system. That's really nice because it's fast, and since .NET can manage its own block of memory, it can also use a garbage collector to clean up everything that is no longer in use, so you as a developer don't have to think about reclaiming that memory or making that memory available again. So that's good. And when memory is allocated in your .NET application, so when you write C# or VB.NET or F#, when you allocate something in .NET, the objects will be allocated in that big block of memory, and the big block is called the managed heap. Now, allocating memory is really fast because, like I said, there's no round trip to the operating system. All that has to happen is that .NET checks, is this block still big enough? If it is big enough, it adds your variable or it adds your object in there, and everything works fine. Now, of course, because there's this big block and it's not really unlimited, the garbage collector has to run over that block of memory to reclaim anything that is no longer in use by your application. So for example, if you have a method and you allocate some code at the start and a variable goes out of scope at the end of the method, you want to reclaim that memory so it can be reused for other things afterwards. Now, this garbage collector releases the objects that are no longer in use, and the way it does that is it pauses your application for a very, very short time. And during that pause of the application, the garbage collector will check everything that is in memory that you allocated in that big block of memory. And whenever it sees that the object it finds can no longer be reached by anything in your code, it's safe to be removed from memory and the block will be freed and you can allocate more memory afterwards. Now, the thing is, scanning that entire block of memory takes time. So it takes couple of milliseconds typically to scan that entire block of memory, but a couple of milliseconds is still quite long in computer language, right? If you have a very complex application and you want really fast results in that application, you still want to reduce the time that the garbage collector has to run. So the garbage collector has been built around that, and this big block of memory is chopped into 3 generations of objects. So when you allocate an object, that object will typically automatically go into generation 0. Generation 0 is a place where the garbage collector runs very often. It runs there, I don't know how much, but it runs very often there. And when it runs, it scans the objects that are in generation 0, and it checks if the objects can be removed from memory, they will be removed. If they can stay in memory, they are promoted to generation 1. Same thing happens in generation 1. The garbage collector will run a bit less often on generation 1. And when it runs, it will also scan the objects that are in there. If the object is still in use, it will be promoted to generation 2. If the object is no longer in use, it will be removed from memory. Same thing happens in generation 2. If the garbage collector detects that the object is still in use, well, the object will stay in generation 2. If it can be removed, it will be removed from memory completely. So that's pretty much how the garbage collector works. The nice thing is that it doesn't have to scan the entire block of memory all the time. It runs the scan or the garbage collection process per generation. So typically when generation 0 runs, generation 1 will probably not run a garbage collection, and so on. Now, I lied a little bit because there's not 3 blocks of memory. There's also a 4th block of memory. The generation 0, generation 1, and generation 2, they are collected, so objects that are no longer used are collected, and they are also compacted. So just like in a defragmentation, the blocks of memory that are removed will make these tiny holes in the memory space. And for generation 0, 1, and 2, .NET will also compact that memory and basically make everything close together, so there's a big block of memory available to allocate new variables in. Now, the large object heap is where big objects go. And such a big object typically needs a lot of space. But big objects typically also have a lot of references to other objects, so it takes much longer to run a garbage collection cycle there. So those big objects, whenever you end up on the large object heap, garbage collection will run. If the object is no longer used, the object will be removed from memory, but no compaction is done. So it will basically stay very fragmented, the memory, after a while. Problem with that is, if you have a lot of large objects, you may run into an out-of-memory exception because there's no big block of memory available for that big object that you are trying to allocate. So large object heap is there. You will always see objects going onto the large object heap, but if you can write your application in such a way that you don't end up on the large object heap, is of course always better. Now, the garbage collector, like I said, runs very often for generation 0. So the short-lived objects run very often. For higher generations, generation 1 and generation 2, typically are slower to clean, so it runs less often for those things. Now, I already mentioned that the garbage collector pauses your application when it runs, and depending on how many objects it has to scan, that pause can take a couple of milliseconds, and I've actually seen application where a generation 2 cleanup took 2 seconds. A couple of milliseconds is probably still okay, but a couple of seconds is probably not where you want to end up with your application. And that's the remainder of this talk. We want to avoid the fact that the garbage collection process may take a lot of time there. Now, of course, there's also background garbage collection. There's a technique in .NET, in the later versions of .NET, where garbage collection is done per thread, so it doesn't have to pause that long, but still you may run into the situation where the pauses take a couple of seconds. And I've heard stories, I don't know if they are true, of even a garbage collection that took almost a minute. So that's also not something that you want to have in your application, because it would mean your application does nothing for that period of time. So the garbage collector typically runs whenever memory is needed. Whenever it sees, oh, the block of memory is almost full, I'll check if I can clean it up to free up some space so that I can allocate new memory in there. It also runs after you do a significant allocation. So if you allocate a lot of objects, the garbage collector will probably run. And I say probably because it's not really documented when it runs, but people have been observing the garbage collector, and typically it runs after a significant allocation. Also, when allocations fail for some reason, when you attach a profiler, when you force the garbage collection, and so on. But the key ones to keep in mind is when in your code you do a significant allocation, so a lot of objects, you can almost be sure that the garbage collector will run and that your application will be paused for a couple of milliseconds, up to a couple of seconds. The garbage collector is also not guaranteed to run, so if you have a lot of memory available, it may not even run because it never runs into any of these conditions that we have there. In case you're interested in the garbage collector source code, you can find it on the internet. And if you look at the garbage collector source code, you will see it's a C++ file that keeps on loading because I think it's about 60,000 lines of code. So it's not really documented, but in case you want to have some bedside reading or something, print out the source code for the garbage collector and see how it works. So it's very, 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 very long. You see the point, right? If in this code, if anyone is crazy enough to read it, please contact me because I would love to know what you learned from that. Right. So the main thing that we want to do is help the garbage collector from making those pauses in our application. We want our application to run smoothly, so let's help the garbage collector to make sure that it can run swiftly and efficiently over our source codes. So a couple of things that we can do is optimize our allocations. A lot of that is being done in .NET Core, for example, right now, where when it makes sense, .NET is making use of an enum instead of a struct instead of a class, because structs go to a different place that is not managed by the garbage collector. Span of T is one. The object pooling pattern is one technique to reduce those allocations. Of course, if you don't have to allocate when it's not needed, then don't allocate. That's also a good way to optimize. But you probably also want to make use of any of the techniques to help the garbage collector. And one of those techniques is making use of iDisposable and the using pattern. Now, I will not go into that in the slides. I will show you some source codes in a bit where I explain how iDisposable works. Another technique that you can use is weak references. And weak references is basically telling the garbage collector that the object that you have, whenever it runs, it can be cleaned. You don't care that it moves on to generation 1 or 2. You just want it cleaned whenever it runs. That's a weak reference. Comes with its own pitfalls because you may run into the case where all of a sudden you have a null reference exception because the object was removed from memory. So it's a bit dangerous to work with, but it's a technique that you could look into. Finalizers is another technique that you could look at, but I would say beware of finalizers because finalizers are the latest moment in the garbage collection process where you can do some cleanup of the objects, which means if you do something wrong in a finalizer, you may introduce a big memory leak because the object may never go out of memory if you do it there. So with that, let's see how we can help the garbage collector. I have a small project here, and by the way, if you look at the slides, there's a GitHub URL there. If you search my name, you find my name on GitHub, you will find this project as well. If you want to run through these projects that I'm showing you at home, there's much more in there than I can cover in this talk. Feel free to download the sources and step through it. I'll wait for the photos. Yeah. Awesome. So let's go into the demo. I have here in this demo, I have an object called sample disposable, and I'll make it a little bit smaller. Yep. And that thing is, for now, let's imagine it is not disposable and we didn't do anything there. So imagine this is my object. My object has a reference to a file stream. So I open a file from disk and I keep a reference to that file in there. And I also create a new integer pointer that also points somewhere outside of the managed process. Now what I'm going to do is in my dispose objects demo here, I'm going to create a list of 10,000 of those objects. So what I'm going to do is create 10,000 objects, add them to the list, and add a reference to that file that I have there. What I'm going to do next is capture a snapshot in the profiler, then clear out that list and force a garbage collection. That's important because I would expect when I run these two lines of code that by clearing the list, I no longer have references to these 10,000 objects. And when I garbage collect, I would expect the objects to be removed from memory. So let's see if that is really the case and if the objects are really removed from memory. So I have been profiling this application using .memory. And in .memory, we can look at the memory usage of the application. So what you see here is the different generations in different colors. And the vertical lines that you see are snapshots where I captured what is in memory so that I can inspect what is going on in the application. So I took a first snapshot right after allocating 10,000 objects. And if I go into the list of objects in there, you will see if I search for sample disposable, if I type it correctly, you will see that there are sample disposables in there, and there's 10,000 of them. So my code worked. I really allocated 10,000 objects. The next thing I did was clear out the list of sample disposables and force a garbage collection. And you can actually see that in the timeline here, that I forced a garbage collection because the memory usage dropped. You can really see the garbage collector ran and did something, but I have no idea what it did, so let's explore that snapshot. If I look at the objects here, and we search for sample disposable, you will see that indeed the list is still there, it's an empty list, but my 10,000 objects are gone, I would think, because If we look at the inspections, we will see that in this snapshot, there are still 10,000 objects of file stream, 10,000 sample disposables in the finalizer queue. So what happened is, because my object has a reference to another object, when the garbage collector runs, it detects that reference and it says, okay, this is too complex for me, I'll move it into the finalizer queue and I'll clean it up later. But that also means that the garbage collector looked at my objects one time and it still has to look at my objects at a later time. So it means the garbage collector has to run twice for something that should be easy to clean up, right? So let's see if we can rewrite that code into something that is more efficient. If we look at our sample disposable, I can implement the iDisposable interface and create a method that does basically this. I destroy my file stream manually, and I free the other reference that I held into this object as well. So I help the garbage collector break that reference and tell it, look, I broke those references already. You can simply start cleaning this thing up. In my demo itself, what I did, again, I create a list of 10,000 of those objects. But before clearing my list, I call dispose on every object that I have in there. So I could also write a using statement and call dispose like this, but this was easier for the demo. So I call dispose, I call clear on my list, and then I force a garbage collection again. When I do that, I expect again that all the objects are removed from memory, and we can indeed see in the snapshot here, you see the memory usage go up again at this point. And when we look into that snapshot, again, you will see sample disposable, 10,000 of them. If we go to the last snapshot, after I cleaned and called .dispose on all of these objects, we can see in the snapshot itself that there are no more sample disposables. So it's only my list that is still there. And if I now look at the inspections here, you will see that the finalizable queue is also empty. So I help the garbage collector clean this up in one cycle instead of 2 cycles. So imagine this was a list of 20,000 or 20 million objects. The garbage collector would have to run twice if I don't dispose manually. If I help the garbage collector, it only has to run once and only pause my application once. So that's a big improvement, and we helped the garbage collector clean things up. All right. Let's look at allocations a little bit. When are we allocating code? That's a very good question. Typically, we are not allocating in the managed heap whenever we use integers, strings, booleans, structs, decimals, enumerations, floats, etc. Those are allocated on the stack, not on the heap. And if they're on the stack, the garbage collector doesn't have to do a thing with it. The only issue is if it's on the stack, you may run out of real memory. So you really want to use the managed heap in some cases. Typically, when are you allocating? Whenever you do a new of an object. And that's very visible because when you look through your code, you see the new keyword, you know, okay, I'm allocating something or maybe something big on, in memory in .NET. Now, next to those visible allocations where we have a clear new keyword, there's also a lot of hidden allocations. So for example, the code snippet that I have here on my slides is boxing something. So I create an integer with the value 42. And that integer is allocated on the stack, so no garbage collector is involved. But the problem is, on the next line, I cast it into an object. So that means that the garbage collector is all of a sudden, it is involved because I'm putting that integer inside of an object box, and that object is a reference type, so it has to be collected at some point. I also added unboxing there, not because it's allocating, but because it's wasting CPU cycles because it has to follow the reference. But unboxing doesn't really allocate, but it's also not something you want to do all too often. Whenever you use lambdas or closures or whatever, there's some compiler code being generated, and that also does some hidden allocations that you may not be aware of. There's params arrays, there's a couple more things, and I'll show you in code a couple of examples of things that you may not expect that would be allocating into the managed heap. So how do you find those things? Well, first of all, like with anything in software development, I think you build experience by doing. So whatever you write in codes and whatever problem you run into, you learn from that problem, and that helps you learn how to do it better next time. You can also look at the intermediate language. Intermediate language, if you don't know, when you have C# and you compile in Visual Studio, you will compile into intermediate language, and only when you run the application, the intermediate language will be compiled to your computer's language. So the intermediate language is much more basic than C#, so it also helps us in spotting hidden allocations if you want. Now, intermediate language is very verbose, so it also gives you long lines of codes, so it's probably not the best way to look into it. A better way is to use a profiler, or if you're using ReSharper or Writer, you can use the heap allocations plugin, and that will show you a nice code analyzer that tells you whenever you are doing a hidden allocation. So let's look into some hidden allocations. If you install ReSharper into Visual Studio, you get a tool window called the IL Viewer. And the IL Viewer, what it does is it shows you the intermediate language of the C# codes that you have at hand. So for example, if we look at the C# code here, and let me resize a little bit. If you look at the C# code here, whenever I click this method, you will see that the entire method is decompiled into intermediate language, and I can look at the entire method and all the statements in there. What's also nice is when I select one statement, the IL Viewer will also update and show you the IL code for just that one statement, and also vice versa. If I select some IL code, it also selects the corresponding C# code. So it helps me translate between the two languages. Now, in the example that I had on my slide where I had the integer that I'm boxing into an object, I can clearly see in the IL code that I'm running a box statement, and if you look at the tooltip for that, it tells you that you are converting something into a reference type, so that's very clearly a hidden allocation. We only see it when we look at the IL codes. Now, there's a nicer example. Let's look at this one. I think a lot of people have already written code like this, where you have a method that takes a params array of strings, an unknown length of arguments to this specific method, right? Thing is, that's very useful because then you can do something like a for each over all that data that you have there, but it also comes with one downside, and that is a hidden allocation. Whenever you call such a method that takes a strings array of params type, so a variable length of arguments, you're actually creating an empty array, and we can clearly see that in the intermediate language code. When we call it without passing any arguments, you will see that we are creating a new array, and here we can see new, so that means we are allocating something in memory. So if you weren't aware, calling your code like this creates an empty array, and that may not be a problem, but if you have a very high traffic application, it causes a lot of allocations to be happening, and allocations, a lot of them, means garbage collector will run and may introduce a pause into your application. I have another nice example here, and let's minimize the IL code here for a second. I have an average within bounds method, and the average within bound method takes an array of inputs, a minimum and a maximum, and then I have a nice link statement that says, from this list of inputs, take all the numbers that are between minimum and maximum, and of that minimum and of that list of numbers, calculate the average. I think that's a very readable piece of code, and link is awesome for making code very readable in this way, especially this type of thing. Problem with link is that link doesn't execute immediately. So whenever we write this statement, we haven't yet executed the codes that we have here. We haven't yet executed that expression. We only execute it whenever we call .sum or .average or .toList or .toArray and so on. So that means in between here, my minimum and my maximum value could still be changed. And when I change the values there, my initial statement is no longer valid. So I want to keep track of what the minimum and the maximum were when I created this link statement, right? So what happens is, if you look at the source code for this in intermediate language, you will see that right before my link statement, so that's my link statement, this is my link statement in intermediate language, right before that, you will see that we have a new object being created. And that new object is of type display class tree, something generated by the .NET framework. And that class holds my minimum and my maximum as an integer. So I've allocated a hidden class without me knowing. I just created readable code, but it still means that I have something that is allocated in memory. And again, it may not matter, but if you have a lot of these, it will matter because you do a lot of allocations and the garbage collector will run. So just to give you some background there. Now, before you go home tonight, and you think, okay, all the source code that I have, this Martin guy said that I should beware of allocations and I should optimize my codes, don't do it. The reason for that is that it may not matter. It may be that the garbage collector can happily reclaim all the memory in your application. It may be perfectly fine the way your application is written. What I want to say is, whenever you think you have a memory problem or you just want to explore, see if you maybe have something, you want to measure before you start optimizing. Measure using a profiler like .memory or .trace, or use performance counters in Windows to look at how frequently you are allocating, how frequently you are collecting or running the garbage collector, and what generation you are running on. So when you see that everything is collected in generation 0, all is probably fine. If you see all of your objects go to generation 2, and you see that the generation 2 collection takes 2 seconds, that's probably a sign that you want to start optimizing your code. So don't just go optimize, always measure first and see what can be improved. Now, in summary of the garbage collector is optimized. So as I said, don't just go and optimize your codes. The garbage collector is really good at what it does, so don't fear it. It's not because I say there's some edge cases that you will run into those edge cases. The garbage collector is what makes .NET work, and it's what makes it pleasant to work with, so use it. But just be aware of when allocations are happening and when garbage is collected and when generation 2 collections pause your application. Measure. Now, let's be geeky and see what is going on inside of .NET. So, how would you, if you would have to start .NET from scratch, or you want to create your name as a new runtime system, how would you build a managed type system in there, so where you have classes and objects, that is stored in memory and that is both CPU and memory friendly? How would you build that? Probably you would go build something that is very similar to a database. You would go with similar or a couple of tables and tables that reference another table. So probably you would think of your memory space like you would have a table that stores information about your type. I have a class named person, so in my table I say I have a type person. Then I have another table that holds, okay, person has 2 properties, name and age. Name is a string, age is an integer. So one table describing what is going on in memory. Then you would have another table probably containing just the values. You would say this type, this row in my database is of this type, and the values are coming from that table. So that's probably how you would design something like that. Now, the nice thing is, .NET is actually created like that. If you look at how the managed heap is structured, you will see whenever you allocate a new object in memory, you will see that you get back a pointer, and that pointer is simply a number pointing to data. The data is a table containing just the values, so it contains my name, my age, and so on. And it also contains a reference to which type is this. So by just looking at the data, I don't know the type, but if I follow the link to the type, I get information about the fact that this is a person, there is a name property, there is an age property, etc. So that's quite interesting. Now, this of course is very schematic, and I want to visualize this a little bit in code, because I don't know about you, but I like reading code because it makes it easier to understand how some things are structured. So let's see if we can do that. And we can actually do that using a library called ClrMD. That's a lot of text. Don't read it because it's a long, long definition. Just remember ClrMD, or Microsoft.diagnostics.runtime, gives you some sort of a link to heap. It allows you to connect to an application and inspect whatever is in memory and look at the different objects, types, how many, and so on. So let's look at a demo there. I have a sample application where I have my ClrMD Explorer, and I will show that in a bit, but I also have an application that I want to look into. I want to run this application and look into the memory that this application is consuming. So what this application does is it allocates a string, it then creates a clock using a using statement, so I'm disposing that clock. In my using statement, I'm defining my timer, and my timer will tick every second and then call my clock's onTick methods. Then I close my using statement, so that means my dispose is being called. And I also run garbage collector.collect, so I force the garbage collector to collect. And I expect, whenever I end up here, that my clock is removed from memory. That's my expectation. So let's run the application. And we will already see when we run that application that we get the time every second, whereas it already said I performed garbage collection, so something is wrong here. My clock is still in memory. I collected, but it's still in memory. What is wrong? So what I want to do now is use ClrMD to connect to this application and see why my clock is still in memory. So in ClrMD, it's a lot of code, but I'll walk you through the important things. ClrMD allows you to create a new data target that attaches to a process. So what I'm going to do is attach to my other application to get insights in the information in memory. I have to call it, give it the process ID, of course, so it knows where to connect. And I also have to give it a flag that says, do you want to just look at the application, how it's running, or do you really want to be invasive and pause the application to see what is going on? I want to go with invasive because that means the application is paused, just like the garbage collector would do, and I can really look into what is happening in memory there. The moment I have such a data target, I can get a lot of things like the current CLR version, all the different objects in memory and so on. So let's maybe run it so we can see what it does. So I start my real application. You see it ticked once, and then this one connected to it, so I now have information about it. First thing we see is I connected to it using some CLR version, not super important in my example. I can look at the runtime info, and I can look at the current threads, but more importantly, I can, for example, dump all the objects per generation. So I used ClrMD to give me information about all the different objects that are in generation 2, for example. So the way this works is that whenever I want to dump my objects that are in memory, I can loop over all the object addresses in my memory space. So remember the tables. This is my first table. I look at the table that contains all the object pointers. For every object pointer, I then get the type. So I make the call to the second table where I get the information about, is this a string, is this a person, which properties does this person have, etc. Whenever I have the type, I can call ClrMD to also give me the value using that type information for the object at this pointer. So this is basically my database call where I select, okay, for this object, give me the value using the information from this type. So this is really joining those three tables together and getting that information. And that code dumped all the objects per generation. Another thing that I can do is walk through it. So right now, I just did a for each over all the objects that are in memory per generation. I could also start looking for my clock, and then from my clock start following the different references. And I could, for example, say, okay, give me which objects are keeping my clock in memory. And you will see that my clock is being kept in memory by a timer callback, then a timer queue timer, and then a timer queue somewhere. If you're creative and in a good mood, you can also visualize this and get a nice visual of how it remains in memory, and use ClrMD to sort of write your own memory profiler to see which object is holding your clock in memory. And in this case, it's clearly a timer callback. Now, I can confirm this in a real profiler that is not using ClrMD. So if I look at my ClrMD target in .memory, and I look at the key retention paths for my clock, I can also clearly see that my clock is being held in memory by this timer callback. So I have to rewrite my code a little bit so that my dispose really disposes of the timer as well, and not only of the clock. So I made an error in my coding, and I introduced a memory leak in this thing. Now, a good question would be, Martin, why? Why are you doing this? Why so complex? Why are you using this ClrMD thing when you have things like .memory where I can easily visualize the memory leak? Why are you doing this? Well, the reason why you may want to look into something like ClrMD is when you discover a memory leak, you want to write maybe a unit test that confirms that the memory leak is A, solved, and B, never comes back again. And I'll give you an example of that. In Rider, I wrote a feature which was actually a memory leak, apparently. So typically, when in Rider you open up a solution, you get all the objects in memory that are related to that solution. So you get the solution, all the projects, all the source code for those projects, etc. And turned out that the new feature that I wrote was keeping one of those files in memory. So one of the code files was kept in memory. which also meant that when the code file was in memory, my entire solution structure would remain in memory because it could not close it because that object was still there. So it meant that if you used that nightly build of Rider back then, so it never was released, but if you used that nightly build internally in JetBrains, well, I'm sorry, I caused my colleagues a bad day because whenever you open 3 or 4 projects, you run out of memory. So that's something that I did wrong. So what I did was I started investigating this memory leak first, and I solved it, but I also wanted to make sure that at least I or another developer could never make that same mistake again. So I wrote a unit test that confirmed this memory leak and confirmed the fact that I solved it. Now, I could do that using ClrMD, but in JetBrains we have a nice project called .memory units, which allows me to write unit tests for memory leaks. This is, by the way, a free tool that you can use, so you can write your own unit tests using .memory for free. And it's really easy to write a test that checks whether an object is removed from memory or not. So let's look at a quick example of that one. In here, again, I have my clock object, and I rewrote sort of the source codes that I had in my previous example. So you will see that I created a timer. That timer is used in a clock, and whenever the clock ticks, by that timer, I call the onTick method. I run that, and then I could write some code using .memory unit that says, .memory, please check that from the memory, all the objects where the type is clock, there are 0 objects in memory. That's the unit test that I wrote here. So what I did is I wrote that unit test. I can run this unit test under .memory units, and I get back the results, and the results will be that, let's wait for it. The result will be that, the result is that, come on. It's coming, I know it's coming. Yes, there it is. So my test failed. I asserted that I expected there was no more a clock in memory, but apparently there is still 1 clock in memory. Now, the nice thing about .memory unit is that it also attaches the profiler to your unit test. So when a test like this fails, you will also get a .memory workspace that you can open, and let's do that. It basically captures all the information from your unit test, and you can then explore this in .memory. So it is starting, and we will see pretty much the same thing that I showed you earlier, where the clock will still be in memory. So there it is. I have my snapshots, all the objects that are in my snapshots. I expected my clock to be removed from memory. And if I look at my clock key retention paths, you will see that my clock is still in memory because of this event handler that is still subscribed to the clock. So what I did in my Rider example as well was I wrote a unit test, or I improved my codes, but I also wrote a unit test that checks whether I'm doing fine. So the solution to this problem was that whenever I wanted my clock to be disposed, I should stop the timer and unsubscribe my onTick methods. Whenever I do this, I can again check my memory, and when I run this unit test under .memory units, we should see that this one succeeds and that I really fixed my memory leak. And whenever someone reintroduces the memory leak, this test will also fail, and I will be aware that someone reintroduced that memory leak in there. So now I'm happy, memory leak is gone. So that is why I showed you what I showed you. So with that, in conclusion, the garbage collector is really optimized for what it does and for high memory traffic. So don't fear allocations. Be happy with short-lived objects. Trust the garbage collector will do its thing. Don't fear any allocations, but do know that generation 2 can pause your application a little longer than you expect them to be paused. So if you have that case, you may want to start looking into optimizing, and don't just go out and optimize. Always use a profiler first. Check if it's really a problem. Check if there is really a problem, and only then start optimizing your own source codes. Measure using a profiler, and whenever you detect a memory leak, it may be useful to also write a unit test, for example, using .memory units, to capture the memory space, see if the object is really being removed from memory, and if it's not, you may want to optimize your code again. But if it is, you can be sure that that memory leak at least is solved and is not going to cause you any trouble later on along the road. If you're interested, I already showed you the GitHub repo where my demos are located. There's much more in there. You can also go to my blog. If you search my blog for memory, you will also find a lot of the information that I gave you in this talk, so you can read it at home and simply walk through it and have some fun with it. So with that, I think we are done here. I want to thank you for being here, and I hope you enjoyed the rest of JetBrains Day. Thanks for coming.